Hi, good morning. This is Miss Litton, and this is my excellent, wonderful, very bright Period 2 Honors Biology class. Say hi.
Hello.
And we are continuing on in Chapter 33, looking at populations, and we are now discussing predator and prey relationships. Now, if you take a look at that graph right there, I'm going to make it just a little bit bigger. And oldest bio buddy, tell them what's going on in this graph. Go ahead, oldest bio buddy. All right, so there's the bunny, the hare, and there's the lynx. And what do you see? What's the pattern? When the hare numbers go up, what happens? Lynx numbers go up, and then when the lynx numbers go up, the hare numbers go down. So they're intertwined, right? They're life. Why is that? Because the lynx is eating the hare, right? That he's a predator on that. Now, why might the bunny numbers, the hare numbers go down? It could be because maybe there's a drought and there's not enough food for him, so his number goes down. But because his number goes down, whoever is eating him, the lynx, their numbers go down as well. So those two tend to cycle back and forth. So on your notes, underneath predator-prey relationships, which is predation, when a predator feeds on a prey. When a predator feeds on a prey. And then you have the cycling, the lynx and the snowshoe hare. And sometimes, you know, like if the hare is running and he's running fast, the lynx wants to be able to also run what? Fast. So let's say the hares get faster and faster and faster. You would expect the lynx to get faster and faster. They're pushing each other because that's its food source. And when you see that, that's called coevolution, when two different species pressure the other, trying to either be a better predator or to be a worse prey so you don't get eaten. And I'm a pin. Okay. Youngest bio buddy, go ahead and explain the coevolution that you see in a predator-prey relationship. Go ahead, young one. So let's look at something you can do. I'm turning off the lights so you can see the next set of pictures a little better. One thing you can do to defend yourself, if you're a plant, is you can have what? Thorns. What's something else you can do if you're a plant to defend yourself? Because you can't run away. Yes.
Like a poison or something.
A poison, a toxin, makes them sick. Any other ideas? What? Poison ivy? Go ahead. Have a shell of some sort that protects you, like maybe a layer of hairs, fine hairs or something, so the bugs can't get in at you.
Maybe have like a relationship with their animal.
Exactly. We're gonna see that in the acacia tree. Their thorns are hollow, and they provide food and shelter in the hollow thorns for ants. So when an herbivore comes over and starts to eat them, then the ants swarm on that herbivore, and so the herbivore goes away. So that is a symbiotic relationship between an insect and a plant, and it works out to both of their benefits. So that's an example of mutualism, and we'll be talking about that. Another thing you can do is you can have something like warning coloration if you're an animal. Why would you be bright red in a very green forest? What are you advertising? Everybody tell me, what are you advertising?
You're poisonous, don't mess with them.
Yeah, you're poisonous. Don't eat the red ones. They make you sick. Okay, and so you want to advertise that fact, and you don't want them to mistake you with another one. Sometimes they hide their warning coloration because they'll try to blend in, and then at the last minute, if they see, oh my gosh, somebody's going to eat me now, then they expose themselves and give that indicator, you probably don't want to eat me. There are salamanders that live in the bottom of rivers, and they try to blend in, but if something comes along to eat them, they flip over and show their underbelly that's brightly colored. Or even a really violent way of protecting themselves. One species of salamander, if they try to blend in, but if somebody comes and tries to eat them, they take their ribs and push them through their skin like Wolverine, like this, and like, you don't want to eat me. And that is a way of an anti-predator defense mechanism. So on your notes, okay, if you look at that, on our anti-predator defenses can result in coevolution, which we already talked about. A, plants have spines or toxins. We talked about that. And then B, this would be referred to, bless you, as warning coloration. Warning coloration. C, you can have poisonous secretions. Poisonous secretions. So if you're walking in a rainforest and you see a brightly colored frog, do you think it would be a good idea for you to pick it up?
No.
No. You know, like, look at that cute bright frog. I want to hold it and then die a few hours later. Okay, so you want to be careful because it's brightly colored for a reason. It knows it doesn't blend in. It knows you see it. It feels like its anti-predator defenses are enough to warn you away. Concealment, sometimes you try to hide. You see little creature in there?
Yep.
It's right here. Okay. Now, what's something amazing to me about this is, do you see the rocks, and do you know what that is that's growing on the rocks? It's very flat. Do you know what it's called? Yeah, it's lichen. And you can see that there are different colors of lichen. It's this stuff right here. That's lichen, and there's a dark one right here. Lichen are in primary succession, one of the first organisms that can help break down the rock in order to create soil. And they're growing all over that rock. And a lichen is a symbiotic relationship between an algae and a fungus. It's mutualistic. It works out for both of them. It could also be a bacterium and a fungus, though some people say it is almost a little bit on the side of like a mafia guy who says, yeah, I'll watch your property, you pay me the money, right? Like, well, maybe you don't really need to watch my property. So, because it's from you. So there's some, maybe it's a little bit commensalistic, maybe even a little parasitic. It depends on the relationship. But the part that's amazing to me is this coloration on the rock, and then look at the coloration on his fur. And then I want you to discuss with your bio buddy, how do you think that came to be? How do you think that came to be? Talk it over with your bio buddy. Okay, so we haven't discussed this yet, but there was a man named Darwin, and he came up with an idea. It's 2 words, starts with an N, and the second word starts with an S. Do you know what that is? Natural selection. So what do you hear in natural? What word do you hear in natural? Tell me.
Nature.
Nature, yeah. So nature was selecting who was best fit for this environment. And any of these guys that had this coloration that just happened to match the rocks, those are the ones that survived and got the most food and had the most offspring. So they had more babies that looked just like them. And then of all that cohort of all those offspring, the ones that blended in best with the rocks were the ones that survived and reproduced and had the more offspring. So over time, it can become very, very specific. So specific sometimes it almost is unimaginable how they could have adapted that way. Okay, look for the caterpillar on the leaf. Okay, if you look right here, here's some xylem, right, on this. This is where the caterpillar's body is. And he has like shaggy like legs right here. Right here is the antenna. Can you see it? So he's going for that concealment. He's trying to hide. He's mimicking that leaf. So those that looked most like the leaf, I mean, you would go right by that and not see that with your eye, right? And it's hoping that a bird would do the same thing. It's trying to blend in. Take a look here. Okay, so you see the goat right here. Here's legs. Okay, so he again matches his rocks so well. And why? Because those that blended in the best were the ones that survived and reproduced and had the most offspring. Okay, when you look here, can you see the bee?
Yes.
But do you see the spider?
Yes.
You see it? Okay. Okay. So you see the spider. So, and the spider, the bee never even saw him. And so he goes in there to get some nectar, to get some food, and be in his mutualistic relationship with that flower and saying, you could give me food, I'll carry your pollen somewhere else. Deal, deal. Okay, sweet. Whoa, spider, dead. Okay? So it works out well for that spider. Now, would that spider survive necessarily in a different flower? No. Why? Because this is the color that matches it exactly. Okay? Now, did he shop around till he found a flower that he blended in with? No. He doesn't know what he looks like, right? There's no mirror. Okay? But the spiders that lived on those plants that were the closest yellow to the yellow of the flower, those are the ones that survived and reproduced and had the most babies. Yes? And that is what natural selection, and that is the greatest contributing factor, though other things can contribute as well, like chance and genetic drift, things like that. But the greatest mechanism for evolution is nature selecting who is the best fit, and you get to survive. Pufferfish. His anti-predator defense is fright. I have a pufferfish right here, hanging from the ceiling. So he's just trying to be, I'm cool, I'm just chilling here, but if something comes up on him, poof, right? And so he tries to frighten you away by puffing up big like that. You see animals do that all the time, right? Even if you had a dog. What are some things an angry dog does, right? Takes their ears, maybe puts them back. What happens to their fur? Yeah, bristles up, trying to look a little bigger, a little fiercer, right? So that is a typical behavior. Take a look at this. This is an insect. Here is his eye, okay, right here. This is really where his head ends. This is a balloon he blows up. You see it? And look what it looks like. It looks like a pissed off alligator, right?
Yeah.
Has he ever seen himself in a snout? Has he ever seen himself in the mirror? No. But the ones who had a smaller balloon, maybe they were using fright initially, and then they, bigger and bigger, it got selected for. So somebody looks at that and thinks, going to eat it, that has sharp teeth, it might bite me. I'll try another insect. Okay? Who selected that? Nature, right? And over time, it became more and more evolved and more specific. Okay? This is on his butt. Okay? On this caterpillar's butt. And do those not look exactly like eyes? Discuss with your bio buddy. Why would eyes on your butt be a good, why would that be an adaptation or an advantage? Talk about it with your bio buddy. Not too loud so other people can focus on that. Okay, now, if you're trying to sneak up, like on a worm that maybe is, or a caterpillar that's on a leaf, it's not like they have a lot of defenses, as a caterpillar. I don't know how to, so basically they're probably going to go for escape. So if something goes, they'll just roll off the leaf and just go, I'm going to chance it, and revenant, you know, just ride your horse right off the cliff, right? I'm going to chance it because this way is sure death. So they roll off the leaf and fall to the ground. That's if they can see it coming. So maybe the bird who's going to eat it tries to sneak up on it. So it comes at it, you know, it thinks, I'm going to come around from behind. So they think this is the head because these are real prominent eyes, right? And it tries to sneak up from behind at the eyes that are not as obvious. And he's like going, oh, he's trying to sneak up on me. You know, and rolls away or something in order to protect himself. He's never seen his butt his whole life. There's no mirrors, there's no way like, oh my gosh, your butt looks so good, okay? He can't, he has never seen it. Yet he has that attribute. Why? Because the ones that had one that looked like eyes are the ones that what? Survive and reproduce and have more babies, right? Over time. There's a frog, I have a little video clip, not here, I wish I did, but a frog, he has eyes on his butt. And when a possum comes up to eat him, he does a couple of different strategies. Who knows why he has eyes on his butt? Maybe if it's sneaking up on him and he can see it and run away, same thing here. But he stands up and just screams. He like gets on all fours. Like normally frogs are like this. He's like up on fours. His butt with those eyes are huge in the back, and he's just like, ah! And he'll just. And the possum's like, no, I don't know. You know, is it worth it? You know, and just scream. So there's a lot of different strategies there. Okay? Oh my God. Now, this right here, this is a fly, but he's trying to look like a spider. Why is it to his advantage to look like a spider? Because what do spiders have? Yeah, poison, fangs. So he will even like try to mimic the way a spider moves on a leaf. He'll try to mimic that. Like, I'm just, you know, I'm just a spider. You know, you don't want to bother me. I'm not a tasty fly. So this is a lie, but it's a good predator defense. He's posing as something he's not. If you look at this is a flower fly. He's a full-on fly, but yet what does he look like? He looks like a bee, because bees are normally black and yellow, right? So he's trying to convey that and say, I have a stinger, you shouldn't mess with me, but he is a liar. He's pantalones en fuego. And he's trying to get you to take, the way I remember that is he's trying to get you to take the bait. That's not why it was named. The guy's name was Batesian who discovered that. But I always try to remember that. He's trying to get you to take the bait. Batesian mimic. I am poisonous. I am tasty, but I'm trying to mimic something that is what? Poisonous. Yeah, that's what he's trying to do. Now, if you take a look here, this is a beetle. You can see that same adaptation. I'm trying to look like a bumblebee or a wasp or a hornet, but I'm really a tasty beetle. But I'm going with the black and yellow. Now, this is a bumblebee. Does a bumblebee have the same coloration as a hornet or something else? Yes. But here's the strategy here. This is called a Mullerian mimic. What he's hoping is it'll increase the learning curve. If we all use the same warning coloration of black and yellow, maybe you'll learn faster. Just leave the black and yellow ones alone. If there's too many Batesian mimics, liars, the gig's up. It's not going to work. Okay? But if you have more that are, you know, bumblebees, hornets, wasps, all of them are black and yellow. They're actually mimicking themselves. We're all poisonous. We just want them to learn faster. The way I remember this one is Mullerian mimic has, there's a double letter in there. What's the double letter? L. I think stinger, stinger. A Mullerian mimic, LL. We both have stingers. We can both hurt you. We're just trying to increase your learning curve. Batesian mimic, I'm trying to get you to take the bait. I really am tasty, but I'm trying to act like somebody who is not. Okay, so on your notes, underneath mimicry, anti-predator defense, where one species resembles another species or something in the environment. Where one species resembles another species or something in the environment. Batesian mimicry, one species that lacks defenses mimics another that has successful defenses. And give yourself an example of that so you remember it, like a fly trying to look like a spider, or a beetle trying to look like a bee. Give yourself an example of that. Maybe that would be a good job for beta. A Malarian mimicry, several different species with the same protective defenses mimic one another. Mimic one another. And so give yourself another example on that, like bees and yellow jackets or something. Okay, I'm thinking of a number between 1 and 20. Share a number with your bio buddy. I'm thinking of a number between 1 and 20. Oh, I was thinking 7. Okay, you got a number? Okay, here is my number. Whoever's closest to my number, pass or play on just speaking freely. I yow, in your own words. We've done I yow before, right? In your own words, you're going to tell them what you know about predator and prey relationships and prey defenses. Try to just bring it up really. The number I picked was 18. So pass or play on that. Yes, absolutely. There's a pass right to the right of the phone. Okay, hopefully you got a chance to discuss that. Okay, I've introduced this topic to you so far. Symbiosis. Symbiosis is a close relationship that exists when two or more different species live together. And we're going to talk about the 3 different kinds of symbiosis. First, let me tell you what it's not. You and I are not in a symbiotic relationship, where I'm giving you an education and you are getting educated in response. Why are we not an example of symbiosis? Yes?
Because we give you nothing.
What?
We don't give you anything in return.
Oh, you do give me something in return. You give me a sense of fulfillment and well-being if I'm helping you, and your tax dollars pay me. Still, why aren't we in a symbiotic relationship? Yes?
We're the same species.
We're the same species. Okay? So these are not the roles we play in our, in our population where, somebody's the hunter, somebody's the gatherer, somebody's the nest maker. These are not different roles that we give. We're one population. When you talk about symbiosis, you have to be at the community level. You have to have 2 or more species that are working together. Okay? And when you talk about symbiosis, there are more symbiotic relationships than what I'm showing you, but the basic 3 is what I want you to be comfortable with. Take a moment, and could I have the person with the lightest colored outer covering, whatever your outer covering is, the lightest color, could you please differentiate between the 3 types of symbiotic relationships? Go ahead. You need water, sweetheart? You want, Okay, so what do all 3 of these relationships have in common? One always benefits. Do you see how it's good for somebody? Somebody benefits. If it's good for both, it's mutualism. If it's good for one and the other one it's bad for, it's parasitism. If it's good for one and the other one doesn't care, then it's commensalism. Have we had a discussion about your dog yet? Okay, about sharing the bed? Okay, so tell your bio buddy, if you have a dog or some pet, what do you consider your relationship with your pet currently? It may not be what you think. Hey, go ahead, have that discussion. Okay, if your pet is alive, okay, hopefully you're treating your pet well, but if your pet is alive, it is getting food and it's getting shelter. Do you agree with that? Yeah. May or may not be getting love, but it's at least getting food or shelter. So it's going to be good for your pet because your pet is currently alive. Yes. Okay? If it's also good for you and you love your dog and your dog loves you and, you know, it's like brings you happiness, and they're doing like all kinds of like pet therapy, and people have their companion dogs, and elderly people are giving them dogs because they have a friend and something to live for. I mean, some people, their dogs are like their family. It's like a son or a daughter to them. It's very close. You know, others it's like it's a dog, whatever. Okay, but if it's good for both, it would be mutualism. If you hate your dog and your dog is, we had a devil dog. We actually called him the devil dog. And he was hideous, and he made our other dog naughty. He started teaching him bad tricks. He kept getting our other dog, who like always stayed in. All of a sudden, they were going on field trips together. We couldn't keep him in. I mean, he would literally climb the fence of the pool, you know, our pool, and get over, and then to get out an easier fence. We're just like, what is wrong with this devil dog? We just hated this dog. And I hate to say this, but he got in the neighbor's rat poison and ate it, and I'm like, I'm not going to the vet. You know, it was very sad for my son because it was my one son's dog, and the other one had the good dog, you know, but I'm like, good riddance. And I just didn't think I didn't think the vet at that point could save him when we came upon him and he's eating this, you know, rat poison. But he was like a parasite in our house. He was causing nothing. It was bad. It was good for him because he had shelter. If you just don't even pay attention to your dog, it's so sad. That would be commensalism, right? So I think I have Oh, hi. Okay, Slate, explain this. It's supposed to be a joke. Explain it. Okay, so they need each other, yes? They need each other. Okay, so this would be a good example of parasitism. I don't know if this is an old man or a dog, but do you know what this is on? Do you know what it is?
Tick.
It's a tick. He's got his head embedded in here, either into this dog or this old man, and getting a meal. So definitely parasitism. An endoparasite, you can see this worm going all the way through, this tapeworm through the intestines. Here, this is an ectoparasite. It's on top of that, looks like a fly. Oh, whoops, sorry, back to the tick. Here's a leech. Now, a leech, actually, I mean, it could be very much a parasite, and they're built to be parasites and be on your body, and you have to peel them off and all of that. But in this case, this is an example of mutualism. And the reason is this person lost their finger, and they reattached the finger, and it's hard to get all the capillaries readjoined, or, you know, because those are just microscopic, 1 cell thick. And so sometimes when you have a reattached finger, the tissue can still die. So they use a leech on the reattached part to suck and draw blood from the rest of the body into that digit. It's sucking that blood in there. And so in this case, thank you, Ms. Litton, for sharing that. This would be an example. Can you see right where they reattached it? This would be an example of what? Mutualism. But usually leeches are parasites. Strep throat, that's a parasite in your throat, okay? Like streptococcus. Here, okay, I switched it. Okay, this is commensalism, good for me, and the other one doesn't care. A good example of commensalism is the bromeliad, and what happens is he's an epiphyte. He lives up at the top branches of the canopy, and he does that so he gets light. As a plant, it's the flowering plant, so he can get light, but he doesn't take anything from the trees. The trees don't mind it being there. It doesn't help him. It doesn't hurt him. He's just giving a leg up so it has access to light. So that would be an example of commensalism. Remember, if I'm going to write a math equation for these, for parasitism, I'm going to put plus minus. Maybe give yourself an example of a parasitic relationship. For commensalism, I'm going to put plus 0, right? Because it's good for one and it has no effect on the other. And a bromeliad would be a good example of that. Okay, this is a mutualistic relationship. What are we going to put for our mutualistic? Plus, good. So we got a monkey and we got an herbivore. Why is this a mutualistic relationship? What's going on here? You know what's going on here? Is he just looking in his ear? No, he's what? He's eating ticks and bugs off of him. So this is a cleaning relationship, and there are lots of cleaning relationships out there that are mutualistic. He gets all of his little parasites removed, and he gets a tasty snack. Here is Nemo living in and amongst the tentacles of the sea anemone, right? So why is this an example of mutualism? Yes? Yeah, that's okay.
Like prongs, and like it provides shelter for the clownfish.
And what? Yeah, so it's good for this the clownfish. Why is it good for the? What's the benefit for the sea anemone? Yeah. On the clownfish.
Wait, are you saying?
Yeah, I'm saying I get why it's beneficial for him. He has a home. The clownfish has a home, and he's protected by the tentacles of the sea anemone. But what's in it for the sea anemone? Yeah.
It's clean, fish is clean.
Okay, I don't know if there's some cleaning that's going on. I'm looking for that. Yeah.
The fish eat what destroys the sea anemone?
Actually, the biggest part of it is that the fish secretes nitrogenous waste, which the sea anemone can use for its nutrition. So by having it live there, what would be its wastes are actually a benefit for the sea anemone. So they both, and it used to be, this was the textbook example of commensalism. Like it didn't help or hurt the sea anemone, but it was really good for the clownfish. But then as they researched it further, then they found out the sea anemone actually does get something from that relationship. But a lot of them, like here, I talked to you about that acacia tree. This is an example of a hollow thorn that the ants can live in. And then if some herbivore comes up, they swarm all over it. So the ants protect their source of food and their home. And it's good for the tree because then an herbivore doesn't munch on it. And the ants are just eating the food that the tree is providing. Bacteria in your intestines. Those bacteria in your intestines right now, especially your small intestines and your large intestines, they're taking up space so bad bacteria can't live there. Okay, and on top of that, they're giving you a couple of vitamins that you don't naturally synthesize. They're making vitamins for you. In return, you're giving them digested food to absorb. So that's also a mutualistic relationship. And if you ever take, and especially girls, because you have good bacteria that run up your urinary tract, okay? And that area is dark, warm, and moist, and things like to grow in it. And whenever you take an antibiotic, you should follow that up with eating, once your antibiotic is done, by eating yogurt. Because you want to create that habitat again where bacteria are back in your intestinal and urinary tract, okay? Especially girls, you want to do that. Okay, another cleaning relationship. Sometimes these can kind of wander into the parasitic lifestyle, because sometimes they'll pull off a tick and then there'll be blood there and they'll keep drinking the blood that's generated there. So sometimes it can become a little brutal. Here's another cleaning relationship. He's inside the mouth. Here you can see this bird cleaning him. Okay, and cleaning up here. And so on your parts where it says, hopefully you put math and an example next to each one of those. So it'd be plus minus, plus 0, and plus plus. Help your bio buddy move them along if they need assistance. Okay, say, bio buddy, you can do this. I believe in you. Finish. Five. 4, go, 3, 2, okay, I'm done. Yay, 100%. Did we get 100% on the last one? No, we didn't, 1%. Okay, so we have 100%. Yay, that's our first 100. I've got it right here, one more. Ask your bio buddy, were you lucky or good? If they say lucky, talk about it so they make sure they understood it. Go ahead, ask them, lucky or good? Okay. Yay, another 100%. That's 2 in a row. You guys are the grand champions of, you're the only class that has 2 hundies in a row right now. Very good. 2. Okay, ask your bio buddy, were you lucky or good? So proud of you. Okay, last topic. Here we go. Ecological succession. It's the organisms in that area changing over time. Do you think you would have different insects if you were at this stage of succession versus this stage of succession? Yes. Different herbivores?
Yes.
Yes. So ecological succession is change over time. It doesn't always end in having large trees. It could end in just grasses growing, like in a prairie. Do you know why prairies don't get a lot of trees growing on them? Anybody? Yes.
Not that much water.
Boom shakalaka. Not enough water to support trees. And that's why their climax community is just a grassland. Okay? So it's going to vary depending on the climatic conditions. But if you will see right here, do you see how they're starting off with soil? They already have dirt. Okay? So that's not always true. Remember we saw earlier those lichens breaking down the rocks? If you're starting with rocks, that's called primary succession. On bare rock, biotic organisms have to somehow create that soil. Okay, that's primary succession on bare rock. If you had a lava flow that went across an area and now it's just solid rock, like in Hawaii, then it's got to break that rock down. So that would be an example of primary succession. Secondary succession would be like if you had a wildfire and it went through and it burned through all the plants, but you still have soil. So secondary succession, that's how I remember that. Secondary succession soil. Secondary succession soil. What if a farmer who lived next to a forest decided, I'm done farming, I'm going to go be an investment banker, and he just lets his farm get overgrown? Would that be primary succession or secondary succession? Secondary, said with a question mark?
Secondary.
Yes, secondary. Why? You know he was a farmer there. What does it already have? Soil. Check with your bio buddy, make sure they understand that right now. Go ahead. All right. Now, when they have fires like in Yosemite, fires that are started naturally, like by a lightning strike, do they go and put those fires out? No. And the reason is, by having that fire go through, it can be a good thing. Yeah, because it burns through the understory, cleans things out. Some trees will not start to germinate unless they've been scarred by fire. So it's like a good thing, even though you have had that dilemma go on. So youngest bio buddy, start at disturbance, work your way around clockwise from disturbance. Explain what's going on. Oldest bio buddy, you're going to have something else. Go ahead. Okay, do you remember the story of Goldilocks? Goldilocks and the... Good, okay. So oldest bio buddy, this is your graph to explain. Right here, I will make it bigger. And assume you want maximum community diversity. Explain, how does this relate to Goldilocks? Go ahead. Find your literary analogy. Assume you want maximum community diversity. Assume this is what you want, maximum community diversity.
Like large frequencies.
Okay, so if this is what you're going for, maximum community diversity because they're the most stable, true or false? You don't want to have very many disturbances. You want to have 0 disturbances. Is that true or false? False. Because if you take this right down here, here's frequency of disturbance, high and low. If you have low disturbance, look, you don't have the greatest community diversity. You want kind of an intermediate amount of disturbance. And then the second one is size of the disturbance. You don't want it to be too large, but you don't want it to be too small. Yeah. You don't want a storm to go through an area and remove all of the topsoil, because that's going to be slow to recover from, right? But if you have an intermediate level disturbance and it happens every once in a while, that actually makes it the healthiest. If you've ever had a new coach on a team, and all of a sudden now with the new coach, they don't have any history with the other players, and everybody has to earn their spot. And so you have to try out, you have to earn that spot, not because you have a history of always having that spot. And as a result, overall, your team might be what? Better, right? Because you have them filling in those spots, the best qualified positions. And that's what can happen here. You get ants in your cupboard, like I did. Now we have a bug person. I was so annoyed, and it went for the soy wasabi Triscuits that happened to be slightly open. What did I do to my cupboard once I saw that I had ants in it? Everything, I burned it, yeah. Took everything out, I changed the shelf paper, reorganized. Now my cupboard looks like, my pantry looks like it's a store, like all the cans are lined up. I love everything, it's clean and perfect, and I just look at it, it makes me feel good, okay? It's the sickness. So yes, that was a lot of work and annoying to clean out my pantry, but now I have a better pantry. So think, would I like that if that happened every day? No, okay? Intermediate disturbance. And then the last but not least, well, then we have one question here. Go to ecological succession, a change involving a series of species replacements in a community following a disturbance. Primary succession is you start without soil. You're starting on rock. And secondary succession, you return a community to natural vegetation, it has soil. And on your models of succession summary, intermediate disturbance can be healthy for an ecosystem. Can be healthy for an ecosystem. And B, it's a complex process. Chance has a great deal to do with the resulting species that colonize. Chance has a great deal to do with the resulting species that colonize. Okay, you guys, this could be your number 3. Nobody has 3 because nobody even has 2. You can do it. I believe in you. One question. I believe in you. You can do it. Commit. I think we have a couple double logins. Oh, darn it. Okay, somebody picked B. Check with your bio buddy. Okay, so still 2 was good. Check with your bio buddy and ask them if they missed it. You definitely want to explain it, but tell them why B is not the right answer. Go ahead. And I hope you're having a great day. Don't forget to review for your quiz now that you have all of chapter 33. Okay, you're important and special.